Our famous star, the Sun, is a 4.5 billion-year-old yellow dwarf star, a hot glowing ball of hydrogen and helium at the center of our solar system. It's about 93 million miles, 150 million kilometers, from Earth, and it's our solar system's only star. Without the Sun's energy, life as we know it could not exist on our home planet. From our vantage point on Earth, the Sun may appear like an unchanging source of light and heat in the sky. But the Sun is a dynamic star, constantly changing and sending energy out into space. The science of studying the Sun and its influence throughout the solar system is called heliophysics. The Sun is the largest object in our solar system. Its diameter is about 865,000 miles, 1.4 million kilometers. Its gravity holds the solar system together, keeping everything from the biggest planets to the smallest bits of debris in orbit around it. Even though the Sun is the center of our solar system and essential to our survival, it's only an average star in terms of its size. Stars up to 100 times larger have been found, and many solar systems have more than one star. By studying our Sun, scientists can better understand the workings of distant stars. The hottest part of the Sun is its core, where temperatures top 27 million degrees Fahrenheit, 15 million degrees Celsius. The part of the Sun we call its surface, the photosphere, is a relatively cooled 10,000 degrees Fahrenheit, 500 degrees Celsius. In one of the Sun's biggest mysteries, the Sun's outer atmosphere, the corona, gets hotter the farther it stretches from the surface. The corona reaches up to 3.5 million degrees Fahrenheit, 2 million degrees Celsius, much hotter than the photosphere. Namesake, the Sun has been called by many names. The Latin word for sun is sol, which is the main adjective for all things sun-related, solar. Helios, the sun god in ancient Greek mythology, lends his name to many sun-related terms as well, such as heliosphere and helioseismology. Potential for life: the Sun could not harbor life as we know it because of its extreme temperatures and radiation. Yet life on Earth is only possible because of the Sun's light and energy. Size and distance: our Sun is a medium-sized star with a radius of about 435,000 miles, 700,000 kilometers. Many stars are much larger, but the Sun is far more massive than our home planet. It would take more than 330,000 Earths to match the mass of the Sun, and it would take 1.3 million Earths to fill the Sun's volume. The Sun is about 93 million miles, 150 million kilometers, from Earth. Its nearest stellar neighbor is the Alpha Centauri triple star system. Red dwarf star Proxima Centauri is 4.24 light-years away, and Alpha Centauri A and B2 sun-like stars orbiting each other are 4.37 light-years away. A light-year is the distance light travels in 1 year, which equals about 6 trillion miles, 9.5 trillion kilometers. Orbit and rotation: the Sun is located in the Milky Way galaxy in a spiral arm called the Orion Spur that extends outward from the Sagittarius arm. The Sun orbits the center of the Milky Way, bringing with it the planets, asteroids, comets, and other objects in our solar system. Our solar system is moving with an average velocity of 450,000 miles per hour, 720,000 kilometers per hour. But even at this speed, it takes about 230 million years for the Sun to make one complete trip around the Milky Way. The Sun rotates on its axis as it revolves around the galaxy. Its spin has a tilt of 7.25 degrees with respect to the plane of the planet's orbits. Since the Sun is not solid, different parts rotate at different rates. At the equator, the Sun spins around once about every 25 Earth days, but at its poles, the Sun rotates once on its axis every 36 Earth days. Moons: as a star, the Sun doesn't have any moons, but the planets and their moons orbit the Sun. Rings: the Sun would have been surrounded by a disk of gas and dust early in its history when the solar system was first forming, about 4.6 billion years ago. Some of that dust is still around today, in several dust rings that circle the Sun. They trace the orbits of planets, whose gravity tugs dust into place around the Sun. Formation: the Sun formed about 4.6 billion years ago in a giant, spinning cloud of gas and dust called the solar nebula. As the nebula collapsed under its own gravity, it spun faster and flattened into a disk. Most of the nebula's material was pulled toward the center to form our Sun, which accounts for 99.8% of our solar system's mass. Much of the remaining material formed the planets and other objects that now orbit the Sun. The rest of the leftover gas and dust was blown away by the young Sun's early solar wind. Like all stars, our sun will eventually run out of energy. When it starts to die, the sun will expand into a red giant star, becoming so large that it will engulf Mercury and Venus, and possibly Earth as well. Scientists predict the sun is a little less than halfway through its lifetime and will last another 5 billion years or so before it becomes a white dwarf. Structure: the sun is a huge ball of hydrogen and helium held together by its own gravity. The sun has several regions. The interior regions include the core, the radiative zone, and the convection zone. Moving outward, the visible surface or photosphere is next, then the chromosphere, followed by the transition zone, and then the corona, the sun's expansive outer atmosphere. Once material leaves the corona at supersonic speeds, it becomes the solar wind, which forms a huge magnetic bubble around the sun, called the heliosphere. The heliosphere extends beyond the orbit of the planets in our solar system. Thus, Earth exists inside the sun's atmosphere. Outside the heliosphere is interstellar space. The core is the hottest part of the sun. Nuclear reactions here where hydrogen is fused to form helium power the sun's heat and light. Temperatures top 27 million degree Fahrenheit, 15 million degrees Celsius, and it's about 86,000 miles, 138,000 kilometers thick. The density of the sun's core is about 150 grams per cubic centimeter, cm3. That is approximately 8 times the density of gold, 19.3 gram centimeter 3, or 13 times the density of lead, 11.3 gram centimeter 3. Energy from the core is carried outward by radiation. This radiation bounces around the radiative zone, taking about 170,000 years to get from the core to the top of the convection zone. Moving outward, in the convection zone, the temperature drops below 3.5 million degree Fahrenheit, 2 million degrees Celsius. Here, large bubbles of hot plasma, a soup of ionized atoms, move upward toward the photosphere, which is the layer we think of as the sun's surface. The sun doesn't have a solid surface like Earth and the other rocky planets and moons. The part of the sun commonly called its surface is the photosphere. The word photosphere means light sphere, which is apt because this is the layer that emits the most visible light. It's what we see from Earth with our eyes. Hopefully, it goes without saying, but never look directly at the sun without protecting your eyes. Although we call it the surface, the photosphere is actually the first layer of the solar atmosphere. It's about 250 miles thick, with temperatures reaching about 10,000 degrees Fahrenheit, 5,500 degrees Celsius. That's much cooler than the blazing core, but it's still hot enough to make carbon like diamonds and graphite not just melt, but boil. Most of the sun's radiation escapes outward from the photosphere into space. Atmosphere above the photosphere is the chromosphere, the transition zone, and the corona. Not all scientists refer to the transition zone as its own region. It is simply the thin layer where the chromosphere rapidly heats and becomes the corona. The photosphere, chromosphere, and corona are all part of the sun's atmosphere. The corona is sometimes casually referred to as the sun's atmosphere, but it is actually the sun's upper atmosphere. The sun's atmosphere is where we see features such as sunspots, coronal holes, and solar flares. Visible light from these top regions of the sun is usually too weak to be seen against the brighter photosphere, but during total solar eclipses, when the moon covers the photosphere, the chromosphere looks like a fine, red rim around the sun, while the corona forms a beautiful white crown. Corona means crown in Latin and Spanish, with plasma streamers narrowing outward, forming shapes that look like flower petals. In one of the sun's biggest mysteries, the corona is much hotter than the layers immediately below it. Imagine walking away from a bonfire only to get warmer. The source of coronal heating is a major unsolved puzzle in the study of the sun. Magnetosphere: the sun generates magnetic fields that extend out into space to form the interplanetary magnetic field, the magnetic field that pervades our solar system. The field is carried through the solar system by the solar wind, a stream of electrically charged gas blowing outward from the sun in all directions. The vast bubble of space dominated by the sun's magnetic field is called the heliosphere. Since the sun rotates, the magnetic field spins out into a large rotating spiral, known as the Parker spiral. This spiral has a shape something like the pattern of water from a rotating garden sprinkler. The sun doesn't behave the same way all the time. It goes through phases of high and low activity, which make up the solar cycle. Approximately every 11 years, the Sun's geographic poles change their magnetic polarity, that is, the north and south magnetic pole swap. During this cycle, the Sun's photosphere, chromosphere, and corona change from quiet and calm to violently active. The height of the Sun's activity cycle, known as solar maximum, is a time of greatly increased solar storm activity. Sunspots, eruptions called solar flares, and coronal mass ejections are common at solar maximum. The latest solar cycle 25, started in December 2019 when solar minimum occurred, according to the Solar Cycle 25 Prediction Panel, an international group of experts co-sponsored by NASA and NOAA. Scientists now expect the Sun's activity to ramp up toward the next predicted maximum in July 2025. Solar activity can release huge amounts of energy and particles, some of which impact us here on Earth. Much like weather on Earth, conditions in space known as space weather are always changing with the Sun's activity. Space weather can interfere with satellites, GPS, and radio communications. It also can cripple power grids and corrode pipelines that carry oil and gas. The strongest geomagnetic storm on record is the Carrington event, named for British astronomer Richard Carrington, who observed the Sept. 1, 1859, solar flare that triggered the event. Telegraph systems worldwide went haywire. Spark discharges shocked telegraph operators and set their telegraph paper on fire. Just before dawn the next day, skies all over Earth erupted in red, green, and purple auroras, the result of energy and particles from the Sun interacting with Earth's atmosphere. Reportedly, the auroras were so brilliant that newspapers could be read as easily as in daylight. The auroras, or northern lights, were visible as far south as Cuba, the Bahamas, Jamaica, El Salvador, and Hawaii. Another solar flare on March 13, 1989, caused geomagnetic storms that disrupted electric power transmission from the Hydro-Quebec generating station in Canada, plunging 6 million people into darkness for 9 hours. The 1989 flare also caused power surges that melted power transformers in New Jersey. In December 2005, X-rays from a solar storm disrupted satellite-to-ground communications and global positioning system (GPS) navigation signals for about 10 minutes. NOAA's Space Weather Prediction Center monitors active regions on the Sun and issues watches, warnings, and alerts for hazardous space weather events. 1. The Sun is the closest star to the Earth. The Sun is a giant plasma ball, inside which thermonuclear reactions take place. It is located at a distance of almost 150 million km from us. Our luminary is a typical G-class star in the middle of its life cycle. Its surface temperature is 5780 degrees Kelvin. Due to this, the spectrum of its radiation is almost white. Yellowish color emerges when its rays pass through the Earth's atmosphere. The distribution of luminaries of different sizes is not uniform across the universe. Therefore, the Sun is actually bigger than 90% of the stars in its vicinity. In addition, it is a benchmark for us. It is by observing it that we judge as for the nature of other similar objects. 2. The element helium got its name from the Sun. When people first tried to determine the chemical composition of our star by its spectrum, they saw the lines of radiation of an unknown element. For some time it was believed that it was present only there, so it was named after the Greek god of the sun, Helios. This substance was later found on Earth as well, but the name remained. Helium constitutes about a quarter of the Sun. Another 73% is hydrogen, and the rest are heavier elements. It is due to the thermonuclear reaction that converts hydrogen into helium that our luminary produces energy. 3. The mass of the Sun is 500 times greater than that of all the planets around it. The Sun makes up 99.866% of the mass of the solar system. This means that it weighs about 500 times more than all the planets and asteroids combined. Even the mass of Jupiter is only 1,000th of the mass of our luminary. As for the Earth, it is about 333,000 times lighter than the Sun. Our luminary could hold 1.3 million terrestrial planets inside. At the same time, the density of our star is about 40% higher than that of water. 4. The Sun has a crown. The solar corona, Latin for crown, is the outer layer of our luminary. It consists of protuberances and various plasma eruptions. Usually these formations are hundreds of thousands of kilometers long. They are longer than the distance from the Earth to the Moon. The solar corona is one of the hottest parts of our world. Its average temperature is 1 to 2 million degrees Kelvin. However, sometimes there are some even hotter spots in it, the temperature of which can reach 20 million degrees Kelvin. The solar corona can be seen from Earth by observing our luminary during its total eclipse. 5. There are spots on the Sun. The layer of the Sun's surface that emits visible light is called the photosphere. There are colder areas that seem dark. You can't just look at our luminary through a telescope, but if you use dark filters, large groups of spots are visible. Sunspots are areas on the surface of the Sun where the lines of force of its magnetic field are twisted and torn. Because of this, powerful plasma emissions, called solar flares, occur in such areas. To study these processes, the Solar Orbiter device was launched. 6. Solar wind can cause magnetic storms on Earth. The Sun's magnetic field is constantly accelerating charged particles called the solar wind. Usually its intensity is too weak to harm people on Earth. But during solar flares, a large number of charged particles can be emitted. Sometimes a large piece of plasma can even break away from our star. This phenomenon is called coronary ejection. When such particles or plasma reach our planet, they interact with its magnetic field and atmosphere. A magnetic storm occurs, which can manifest itself in the form of auroras borealis. Such storms can cause failures of electrical and radio equipment, and indispose people with chronic diseases. 7. The activity of the Sun changes periodically. Sun flares occur chaotically, in the sense that no one can say for sure when any of the spots that are currently on the surface of the luminary will explode. Perhaps there is some mechanism behind this that we do not yet understand. But the general number of spots is subject to a certain rhythm. There are regular 11-year cycles, each consisting of one maximum and one minimum. Now it is the 25th cycle since the beginning of observations of our luminary. The next peak of its activity will be in 2025. Scientists do not know what causes such a periodicity and whether the period of fluctuations changes over time. 8. Complete solar eclipses will not take place forever. A solar eclipse is a situation when the moon stands between the Earth and the Sun and obscures the luminary completely or partially for a certain part of our planet. The orbit of our satellite is inclined relative to the plane of the ecliptic, so it does not happen every 29 to 30 days, the duration of the full cycle of lunar phases, but 2 to 5 times a year. A total eclipse of the Sun occurs when the moon obscures our luminary completely. There are also partial and annular eclipses. The latter are observed when our natural satellite is in the far part of its orbit and its disk becomes too small to cover the whole of the Sun. In about 600 million years, total solar eclipses will stop occurring. The moon will gradually move away from us to a distance at which it will always look smaller than the Sun. Then only partial and annular eclipses will be observed. 9. In summer, the Earth is farther from the Sun than in winter. The Earth moves around the Sun in an elliptical orbit. That is, the distance to it increases or decreases during the year. However, the change of winter and summer is not related to this fact, but to the inclination of the axis to the ecliptic. So when summer comes in the northern hemisphere, winter comes in the southern hemisphere, and vice versa. At the same time, the Earth passes the perihelion, the closest point of the orbit to the Sun, in January, when it is the middle of winter in the northern sphere. And it passes the aphelion, the most remote point, respectively, in the northern summer. This year the latter will occur on July 4. 10. The Sun emits not only visible light. Like all stars, the Sun emits a wide range of electromagnetic waves. Of these, our eyes are able to perceive only a small area from 380 nanometers, purple, to 740 nanometers, red. If you move further in the direction of increasing the wavelength, you first get to the range of infrared radiation, and then, radio waves. When the wavelength decreases, ultraviolet light comes first, most of which is eliminated by the atmosphere, and the rest gives us a tan. Then X-rays come, and finally, gamma radiation. All these frequencies are radiated with varying intensity by the Sun, and we can learn more about our luminary in some invisible parts of the spectral range than in visible light. Therefore, much of the space and terrestrial devices that observe our star do so beyond the colors available to the human eye.